Okay, Assalamualaikum and good morning everyone. So again, let me remind you your assignment should be out by today earliest or tomorrow. Okay, and then your not final, your first test will be on Thursday. Okay, so presently I'm just a bit busy at the moment. Okay, so as I said before the recording starts, I will do this lecture on the whiteboard. Hopefully, you will be kind to me. Can you see the whiteboard? Okay, great. So let me start. Okay, so I'll scribble a few things so that this is coming from chapter. Let me see. What chapter is this? Chapter 4. So I will get your chapter 3 notes up soon. I've already typed most of it. I have only one section left to type out. Okay. So today we'll talk about statistical mechanics. Okay, I need to do something about this. Let me just check. Probably I will need this on my a bit more slowly, I suppose, so that things are clear. Statistical mechanics. So we're going to look at some of the foundational ideas for us to start this. This is better. So I cannot write very fast. So remember, recall end of lecture 5. There are several questions that was posed that was not really answered. So this is unanswered questions. Sorry, this will be slightly slow. I wanted to do it fast, but the tab is probably the response is slow. So one the unanswered question is, so question here is, what is the microscopic basis of entropy? Okay. So entropy is a state function that we have introduced in thermodynamics, but no, you don't really have a feeling of what is actually entropy in that sense. So today we are going to answer in part, I suppose not fully yet, what would be the so-called the underlying ideas of entropy from a microscopic point of view. Okay, so it comes through Boltzmann. So Boltzmann is essentially the father of statistical mechanics. There are two ways to introduce statistical mechanics. Last semester I used the Boltzmann equation, but this time we use this hypothesis. Where what it says is, remember we have done probability before, so entropy of a system is related to the probability of its state. One has to define what the state is supposed to mean, but let me just carry on without the definition first. Probability of its state, excuse me, and it's supposed to be and it is statistical. So in a way, being statistical, if you remember the two different types of probabilities that we have introduced before, the classical and the statistical, this would require some kind of a well-defined limit. Because remember, we talked about statistical probabilities is like taking relative frequencies, but you know that relative frequencies, when you do sort of finite number of trials, it can fluctuate. So, and in this particular case, it must have a limit when n goes to, the number of trial goes very high, and this can be obtained when this well-defined limit. This happens when when the system is in equilibrium. So in other words, you can actually do this if you want to. But doing this would require sort of making sure that your measurements are if possible, you can completely define all possible states in that sense, but one should consider the simplest case. And the simplest case is when it happens at a particle level. So let us do that. Go to the simplest case. So here's a few points here. State of system. Okay, as I said, there are you need to be able to define them. Okay, is specified as completely as possible. And for a macroscopic state, we will talk about macroscopic state later, then this is not really possible. So let me do this as completely as possible. But if you go down to the atomic level or the particle level, the simplest state, or sometimes it's called a microstate, simplest microstate, okay, is given by what is now known as the quantum state, okay, of the particle, is given by the quantum state of constituent particles. Push this up, oops, no, down. Okay. So, but what is a quantum state? We probably have to defer this a little bit later to really define this, what it is. Let me just check. Have you done quantum mechanics at all?
Yes.
Okay, great. epsilon. Okay, so in other words, I will not have to introduce too much, so I will just give you the sort of key concepts, and you probably can recall from the quantum mechanics course. Okay, so what do I do here? Right, but actually the idea of Boltzmann is, no, Boltzmann lived sometime in the late 19th century, and at that particular time there was no definition of a quantum state, because quantum mechanics or quantum theory happens in the 20th century, right? So really at that time, what's actually possible for Boltzmann to consider is, okay, we will consider the case of classical mechanics. So here, this is slightly different from what's in the book, but just trying to recall that you can actually define states even in classical mechanics. Okay, classical mechanically. Okay, classical mechanically. So I really have to write slowly. The microstate of a particle don't fail me. The microstate of a particle is given by the pair of position vector and the momentum vector. Okay, and the set of points X and P form a space what is known as the phase space. And I believe you have also done classical mechanics, right? Audio feedback, please. I can't see you. Classical mechanics, have you done it? Tengah ambil. Okay. So there are okay. Let me go just a little bit just to summarize what's there in classical mechanics. Classical mechanics sort of what you call normally you learn classical mechanics from schools, in fact, in the form of Newtonian mechanics. Okay, so Newtonian mechanics, you know all this, the three different laws, but there are essentially the Newtonian mechanics are what we call a phenomenal. The laws are phenomenological. Phenomenological, meaning the laws that you hear about Newton's law are coming from observation or from experiments. But a more mathematical framework for classical mechanics, so this is all classical mechanics here. So I'm using the freedom of now being able to write vertically as well. Classical mechanics here. So all of these are classical mechanics. There are a new mathematical framework that you should learn later on when you do classical mechanics courses, is that you will learn it. There's a better way of describing Newtonian mechanics in mathematically in terms of some function called Lagrangian. So you have a Lagrangian given by the symbol L, and essentially this is a function of Q. Q is what we call the generalized coordinate, the position, for example. Then Q dot is the velocity, and it can also depend on time directly. And your state over here is defined by the pair of Q and Q dot. Okay. And then there is a alternate formulation, which is equivalent to this Lagrangian mechanics called Hamiltonian mechanics, where this is described by the Hamiltonian function, and the Hamiltonian function is a function which has the position as well, the generalized coordinates here, and then your momenta in replacement of this velocity here and t. So your state here is given by the pair of Q and P, which is the one that I'm using over here. Can you see the cursor here? Somebody? Okay, great. Oh, that would be good, because I don't need to scribble all the time, right? So in a way, all of this exists at the time of Boltzmann, and one can actually define one can define idea of a state or microstate with respect to these points inside your phase space. Okay, but these are actually a difficult thing to do, because you have in a phase space there are infinitely if you think of what this is, okay, this is X is belong to R3 three-dimensional space, and P is also belongs to three-dimensional space, and there are infinitely many points inside your three-dimensional space, and if you take the pair of this will be in six-dimensional space. Okay, so in other words, the difficulty with that is usually you have to how should I say, you have to consider this infinitely many points that you need to consider. Okay, and one of the difficulty that I had to introduce Boltzmann equation in the last 2 semesters is because you have to do all these infinite dimensional problems. So this time round, okay, we do it simple according to this particular book. So what's wrong with this thing? What is besides the infinite dimensional thing, which we will also see inside quantum mechanics? What is wrong with this is the fact that at the quantum level, push this up so that I can write it better. At the quantum level, if you have done understood quantum mechanics properly, you know that the pair X and P cannot be determined can it be both determined precisely? Because of what? Can anyone remind me? Right, that's good. Determine precisely. I have to write slowly, otherwise no. So one needs a alternate description of a microstate. So here the states will be replaced by generally is you talk about wave functions, but even wave functions is very specific. Okay, one can talk about so wave functions are specific realization. Hope you learn all this. Realization. But you have, since you have learned quantum mechanics, then I can write this thing down. Quantum states can be described as abstractly by the vector cat. Have you seen this symbol before, right? Okay, so and these states, okay, one can use cannot use what you call, at least at the fundamental level, okay, cannot use statistical probability because they are at the fundamental. Okay, maybe I should put the provisor here at a fundamental level. So one has to resort to the other probability that we have learned, which is the now this is a bit odd. The book calls it classical probability. Okay, so one applies apply again. I have to write slowly here. Classical probability, which is what? Which is just saying that no, you assign equal probability to each we'll talk this a bit more later on, to each quantum state, which is accessible. It's a bit difficult to define this precisely, but no, when you go through it, then you start understanding. No, there are various notions of states, which I will just talk in a minute. Okay, let me just finish this sentence. So if there are W quantum states, available, accessible, so then each state has probability 1 over W. Okay. Now, the other confusion is the fact that the concept of states appear in sort of in a hierarchical kind of level. So there already you have seen the way I mentioned about state being microstate, or and also you have already heard about thermodynamical states. So what happens in this particular case when you do this, statistical mechanic kind of formulation of physical system, you often consider ensembles of identical repeat systems Now, how do you define identical in this particular case? Usually through some microscopic variable. For example, in this case, you can say that, okay, I want the prepared system to be all of equal energy. So energy, again I cannot write very fast, equal energy or equal volume. What's the other one? Volume and equal volume or equal number of particles. Later on, we have specific names for all this, okay? For this ensemble, number of particles. Let me push this up. Oh, I'm going the other way. Hello? Slash. Oh, okay. All right. Okay. Hopefully that works. So, okay. So you consider all these identically prepared systems, and you can think of it as a constraint. Okay, it's subject to some give you macroscopic constraints. That you want to know when you consider all possible different states and all possible trials of making measuring outcomes, and then you need this identical prepared systems, okay, so that you can do the relative frequency thing. And so this specification of these constraints or such constraints okay, it used to be called again I cannot write fast, used to be called thermodynamical states. Okay, so one need to differentiate. There are two types. Okay, two types. One is the quantum states. Push this thing up. One is the quantum states, okay, which we'll consider, okay, and they are sometimes called microstates in some books, okay, and then you have your thermodynamical states. States. Cannot write very fast. Thermodynamical states, which are called macrostates. Now, in the book by Bowley and Sanchez, they silent the microstates. They just talk about quantum states and prefer to use macrostates to differentiate it with the quantum states. Okay, but the idea now is to consider your quantum states within a particular now it becomes harder now because I'm trying to write fast, within a particular, so quantum states accessible, cannot write fast, accessible within a particular macrostate or constraint. Okay. So please do it differentiate between the two, and but most of the time we will just talk about quantum states. This is going very slow. So okay, so you want to introduce the microscopic basis of entropy. So let's suppose now we consider, okay, you have this consider, so that finished the sort of the description of the states. So now we consider W accessible quantum states. So when it means accessible here, meaning it will conform to a particular constraint. Okay. So if it's outside this constraint, you do not consider them. So there might be more quantum state than this W accessible quantum states. Okay. I hope it doesn't confuse you too much. So Boltzmann's hypothesis require that that your entropy is a function of this. So here is a function phi of this accessible quantum states. Okay. So phi to be determined. Push that thing up. So, and you have learned about entropy. Okay, one of the things that we learn about entropy, if you have two systems, A and B, and they are not really interacting, and each will have their individual entropies. Individual, come on, entropies. So I can write, for example, the entropy for system A as A would be, it has to be the same function because you need to describe it, your entropy as a state function in such a way it's supposed to be universal. Okay, so here then you have the same function phi that you assume over here, but now it depends on the accessible states inside your system A, and then SB would be the same function, but now it's a function of the accessible states in system B. So but then if you combine the two systems, A and B, as a single, slowly, okay, as a single system, then one can assign this composite system as the entropy as A, B, and it will have to have the same function phi that depends on the microstates or quantum states in the composite system. So we write this as WAB. But since the systems are not interacting and they are considered independent of each other, we learned already it's like the independent probabilities, okay, before. So the two systems are independent because, so this is because of independence of two systems up so that my handwriting gets doesn't get horrible. So then your microstates WAB has to be just a product of your microstates in A multiplied by the number of microstates in B. Okay. So this is like your independence, your independent probabilities before. Okay. So, but then you need all this to happen in such a way that your entropy, I've forgotten to mention this before this, entropy is extensive, meaning if we combine two system, it will grow in as an additive property. Entropy is extensive, so meaning SAB must be equals to SA plus slowly SB. So now we can start to, okay, combine these two equations. So you have this equation here and this equation over here. And remember that your S is what before? Phi W, right? So we combine these two equations. So in other words, what we need is phi. This implies phi WAB, okay, which according to this will have to be phi WA times WB, and this has to be equal to SA plus SB. So that means this will have to be phi WA plus phi WB. So this function has this peculiar behavior such that it takes a product, okay, a product of these variables, and then it can separate out as two terms with an addition sign, such that these variables will appear in one term and the other variable appear in another term. And you already know what kind of function that's supposed to be. Solution, that's a log function. Okay, so log function will do the job. So one can define phi W to be equals to KB, which I'll define in a minute, log, the natural log I'm using over here, of W. What is KB? KB is called, it's a universal constant, it's called Boltzmann constant. So better bring this up. Okay, so in other words, your Boltzmann hypothesis just now is gives you this famous formula of Boltzmann. I think I'm not sure whether you heard the story of Boltzmann got very depressed. Have you heard about that story of Boltzmann? Anyone has read something extra?
No.
Okay, Boltzmann is a very careful scientist, living in the age of where people talk about thermodynamics. Okay, so Boltzmann tried to give a microscopic view of thermodynamics, but there was this school of thought at that point in time where they think all this idea of particles, atoms and things like that are all fictitious, meaning it's just imagination of the mind. So Boltzmann theory was not adopted by a certain school of thoughts. The other school of thought are essentially they talk more about like things in terms of energies that you can define properly through experiments and things like that. So Boltzmann got very depressed. Okay, he got very depressed, and he committed suicide. So this is one of the depressing stories. He committed suicide, and I think on the graveyard was engraved, if I'm not mistaken. Okay, I have to check that story carefully. It was engraved this particular formula. Okay. So never look down onto your onto others. They can get depressed. Okay. Right. Okay. One of the problems with this is you have to still define how do you get all this W thing. Okay. So one of the things that Einstein did was to consider, okay, maybe we can do this in a simplistic way. Well, I mean, his ideas are not simple, but here you don't really need quantum theory as yet. Okay, one consider, for example, the case of non-interacting molecules. Please, okay, non-interacting molecules. After a while, it gets the response is getting slower and slower. Non-interacting molecules in a volume V. Okay, it's getting horrible now. And what it does is, okay, you want to consider all these molecules inside this volume V, and somehow one needs to arrange these molecules in that volume. So what is the next step to do is to consider a subdivision of your volume, subdivide volumes into smaller volumes, into cells. Okay, slowing down, into cells of volume. Okay. It's getting bad now. Volume delta V. So now here is where the combinatorics comes in. You have learned, we did mention combinatorics before this. So now one consider the number of ways of placing one molecule, and I will emphasize one first, of placing one molecule in the volume. So you imagine this volume V, which is a massive volume, and then you subdivide in terms of these smaller volumes, then the number of ways are just simply your V divided by your delta V. Okay, so that will be the number of cells inside that volume V. So it doesn't matter. So you just need to see how many cells that you have in that volume. So the number of ways that you can put one molecule inside there is just V, is just the number of cells. Okay. So now consider number of ways. Excuse me. Number of ways of placing n particles or n molecules in V. And placing of n molecules in V, each molecule is going to be independent of each other. Okay, so it's an independent process. So, independent process. So the number of possibilities or number of arrangements that you can actually have will now be just the power of that. Oops, don't fail me. Okay, that now you apply Boltzmann hypothesis. So you consider this as the number of states that is possible. Apply Boltzmann's hypothesis. So you take the KB log of that. Okay. And KB, the log of that, is the log of this power. So it becomes n KB log of V on delta. Okay, so in other words, it now becomes expressible as in terms of the number of particles. Okay. The only problem with this statement is now, okay, this delta V is arbitrary. Because I can create cells very small or very large. Okay, so how can we remove that arbitrariness? Go to my next piece of paper. Okay, the trick is to recall when you, it's now getting difficult to write now. Recall that you only measure differences in entropy. So this is how slow I have to write. Okay. So what one can do is now, okay, let's do a process. You allow your volume to change. Volume changes. Going from, say, an initial volume to from initial volume Vi to final volume Vf, but keeping the cells constant. So what's going to happen is that you'll be able to write down using this formula the change in the entropy, because that is the one that you can actually measure. Come on, yeah. Delta S equals to the final entropy minus the initial entropy, and this can be written as, using the formula above, NKB log VF over delta V minus NKB log VI over delta V. And you can see here is really an addition of two logs. Well, it's a subtraction, but you can now rearrange that, and you finally get this formula, NKB log of VF divided by VI. Okay. And you can see now, okay, the arbitrariness of the formula coming through this delta V, since delta V doesn't appear here, it only appears, the only thing that appears is the final volume and the initial volume. So it now becomes well defined. Okay, and this you can actually measure experimentally. So that is good. And to make some connections with known things, so earlier we have talked about all this relationship between entropies and the thermodynamical variables. Earlier we know about your partial derivative of S, the entropy, with respect to V, for example, change in V. Usually you keep the internal energy constant there, and this would be equals to P over T. Or you can write this as P equals to T ds du. Okay. So now what we want to do, we want to use the thing that we had before, the expression that we get, which doesn't depend on your volume of the cell. We want to use that, and we're going to write it in this way. So write this Ctrl Z. Maybe I'll put this up a little bit. Write S to be, since you do not want it to be written in terms of your volume of the cell, you will write in this way: S equals to NKB log, where your final volume is going to be an arbitrary volume, okay, V. So that this function now is this entropy is essentially a function of the volume, okay. So NKB log V over your initial volume, we just write a particular reference volume. So V naught here is a reference volume. So this is fixed. Reference, oh please, reference volume, and this is fixed. So the only variable here is essentially your V, okay. Actually your N is also a variable, but okay, in this particular case we just want to concentrate on V. And okay, so let's do the derivative, right? We have this derivative. Oh, what am I doing? Okay, let me rub that thing off. This is wrong. Oops. Okay, never mind. This is ds dv. Okay. So now what one does is to take the derivative of s with respect to v, and this gives you, okay, this just gives you n kb. The derivative of log gives you 1 over v. Okay. Remember that one can separate out the v naught, so you have none. So this becomes nkb log v minus nkb log v naught. So that nkb log v naught is a constant, so you don't bother to look at it. So you just have that thing, and then this gives you p equals to nkbt divided by v, which is what? Oh, don't fail. Okay, it's not moving now. Okay, I'm getting into trouble now. So this is equation of state for your ideal gas. What is happening? Okay, it's moving. So okay, that's great. We get to something which is now we have something familiar to us. And let's consider, okay, remember that kb is not really known at this particular stage. Okay, it's just a constant that was conjured to give you the formula of your entropy. So now one can relate this with what you know with ideal gases. For example, for 1 mole of gas, you have PV equals to nRT. Okay, if there are n moles, then we have this small nRT, but now we write it as RT. And from this one, from there, from star has PV equals to n kbt, where your n is the number of particles, okay, or number of molecules. But now, what is the number of molecules in 1 mole? Number of molecules, number of molecules in 1 mole, number of particles in 1 mole, n equals to Na, the Avogadro's number. So if you compare these two things, then I can now determine this Boltzmann constant from comparing these two equations, the equation of 1 mole of gas and the equation according to the number of particles. So I will get Kb to be equals to the gas constant, which you can measure, divided by your Avogadro's number. So all of this can be determined. So come on. Okay. So that's great. So you get to something which is much more definite now. Okay, you begin with all this number of states according to the cells, and then you remove the volume of the cells. You just look at the entropy change, and then you get a function of entropy as a function of volume, and suddenly be able to use the Boltzmann form of entropy, and then even determine the value of your constant there, which is great. Okay. And there is another case which was mentioned in the book. I just mentioned it briefly over here. You can also apply this PV equals to N KBT thing to osmotic pressure, which is things in a solution, okay, or particles in a solution. But I don't want to go into that. And this was, in fact, even known before Einstein. Okay, so this was known by an earlier physicist. So I will not go into that. Okay, so probably at this stage, before we go into the new things, maybe prompt for any questions at this stage. So I'm following closely in the book. So some of the things that I see, I try to rearrange things so that it becomes more clear. So you can see slight difference from what I've given you on the whiteboard just now with the one in the book. Okay. Okay. Perhaps let's take a break. Do you want a break, or do you don't want a break? Okay, let's take a break for say 5 minutes. Is that enough? Okay. All right. Okay. Are you all back? So can we start back? This will probably be short because I've not prepared too much about this, but I can tell you what I know. Okay, so the next thing is to go into details about, okay, if you see what we did just now was not even mentioning about quantum states. You are just subdividing your volume into cells, and then you look at the number of configurations of of the way how you arrange particles inside those cells. Okay, so one should be really doing delay. One should be doing description of how to do this with quantum states. Okay, be good. Quantum states. So what are quantum states? Since you already know, you already done quantum mechanics, states are defined by solving Schrodinger's equation. So these are states, and the other thing that you know in quantum mechanics is that your physical quantities, your states are not physical quantities, but your physical quantities in quantum mechanics are now defined separately from the states. Okay, unlike the case of the classical mechanics. Classical mechanics, you can see the states are comprised by this pair of position and momenta, which are themselves physical quantities. So here is actually different, and things gets a bit more complicated by the fact that there is this separation between physical quantities and states, and the fact that one need a kind of an abstract idea of a state. Okay, so that is actually the one of the things that a bit difficult for people to comprehend a little bit. Okay, so physical quantities are defined by operators. Okay, and usually we don't call physical quantities, we call them as observables. Why why do we want to change the name in some sense? Well, the fact that observables themselves are not, no, if we talk about physical quantities as if there is already a number associated to no, this set of objects, okay? Because the word quantity signifies that you can assign a number. The word observable, there's no quantity inside there, but what is mentioned over here, you can only observe those things, okay? And there are one of the things that makes it a bit difficult for people to understand is that it is represented by operators. So now, I'll give you an example. The most obvious example is the Hamiltonian. So again, it's a bit odd that you heard about Hamiltonian before going to Hamiltonian mechanics. Okay, Hamiltonian operator, okay, that represents energy. Oops, I was getting horrible. It's given by this differential operator, and usually when we talk about operators, you have this hat. I probably don't need to emphasize too much on this because you have seen this before, I hope. So you have this thing which is a second order derivative here. So I'm doing it in one dimension. Okay, so there's only a variable x, and then you have another one which is a function of x. So this one corresponds to your kinetic energy. This one corresponds to your potential energy. Okay, and you can see this one is probably almost the same as a function, but it's really an operator. Okay, I can write this differently if I want to. I'm not sure whether you have heard about momentum representation. Then this will be a differential operator, and this will be like a function, a quadratic function. Okay, so but anyway, the whole thing is that you have these operators to represent physical quantities. Okay, and what happens when you do this, you have the states. Okay, so the operators act on states. So generally, when they act on states, states are given by wave functions normally. Okay, so consider example here. Given a function phi of x as a Gaussian function over here. Oh, come on. Okay, and if you just take and let's consider the case where v is 0. So there's only the Hamiltonian only consists of the kinetic energy. So in other words, if you try to act h on this wave function, this is a perfectly well-defined wave function. You can normalize it. You have done normalization. Okay, you can normalize it, and if you act on this wave function, what does it give you? So it takes the different. It takes the second order derivative of that Gaussian function. Okay, and it produces this function. Let me put this up, otherwise my handwriting gets horrible. which if you look at it, this is a quadratic function. This is the original exponential function, the Gaussian function. So a quadratic function multiplied with this Gaussian function, it gives you a different new wave function. So in a way, it mimics a little bit of the process that's done in quantum theory. When you measure something, okay, the physical system is in a particle state. When you measure something, you introduce changes with respect to the state. Okay? So in this case, let's call this wave function psi. So the state changes from what? The state changes from phi x to psi x. Okay. So the introduction of this operator is sort of mimics a little bit what actually happens physically, so that when you do measurement, in this case energy measurement, it actually changes the quantum state. But so you wouldn't want to do that when you do calculation. Most of the time you will look for what we call eigenfunctions. So consider, for example, let's say an operator A here. So it acts on so-called the eigenfunctions, which is going to be specific. Okay. So in this case, maybe your A is your H before that. Okay. And your eigenfunction should give you, no, it will produce the same function multiplied by a constant, and this is called the eigenvalue. And this is the eigenfunction. Okay. Eigenvalue of A, eigenfunctions of A. Okay. So what's the good thing about eigenfunctions is that when you do measurement, when you do measurement on this particular state, okay, let me write this in full so that all the statements are there. So when one does measurement of A, okay, slowly now, of A on the eigenfunction, how should I say, it produces as an outcome alpha I, if you measure on this particular state with certainty. Okay. And because of that, okay, these eigenvalues are sometimes called eigenvalues of A, are sometimes called spectrum of A. So what experimental measurements can give you are just your eigenvalues. Okay. Okay, let me move to a more specific thing now. So for example, okay, in the one before, for example, so you know that this is not an eigenfunction. So here phi is not eigenfunction of h. In fact, an eigenfunction of h over here is a bit more complicated because one should be doing a plane wave function. So eigenfunction of h, for example, are given by plane waves. Oops. Plane waves with energy, for example, h bar squared k squared or 2m, where your k is your wave number. But the eigenfunction is what? The eigenfunction will be actually something of this form. Okay, so this is a plane wave, and this is actually unbounded, so it causes a problem. Okay, so what we wanted to do is probably look for a much more simpler problem than those involving plane waves. We look for the case of a bounded system. And bounded systems, in a way, one of the characteristic bounded quantum systems, okay, one of the characteristics of it is that you get a discrete energy spectrum. So that makes it easier because now the energy eigenvalues are actually countable. So it goes from, say, the lower state to the next excited state, second excited state, and so on and so forth. So that introduces a little bit of simplicity than those of the plane waves above, okay, where things are, your k are continuous and it causes actually a problem. Okay. But let's not go into that. Okay, so let's consider the simplest case of a bounded system. This is quantum here. So the simple example here is particle in a box. And to make it even much simpler, particle in a 1D, one-dimensional box. So what does it mean by that? Is that your box are just in an interval. Okay, here, let's say from 0 to L, and the particle is just constrained to move inside this box. So you probably have you probably know how to solve the Schrodinger equation for this. So what you get is that you get the solutions. If you try to solve this, for example, h phi n equals, this is what we call the time independent Schrodinger equation. Okay, so you get your phi n to be b sine some constant, normalization constant there, times n by x over L. And this n is an integer. It corresponds to, essentially if we have done this, then you know that that integer comes from how to fit standing waves inside this box. Okay, so and it's not arbitrary. It gives you the only precise wave number that can actually fit that length of the box. Okay, and if you look at that and try to solve this, your En is essentially given by H. Come on, go up a little bit to Z. H bar squared, what was it, pi squared n squared over 2ml squared. So we are going to consider this kind of problems instead of the continuous one because they are simpler to handle, and probably let me just see what else do I want. Okay, maybe I introduce this spin thing first. So okay, the other simple thing that one can introduce is the idea of spin. So again, have you done spin in quantum mechanics? Anyone? Did you do spin in quantum mechanics? Because sometimes quantum mechanics are broken up into two different courses. Spin might not be included. Have you done spin or not? No or yes? No. Okay, then I will just introduce. But you probably have heard about it. Okay, spin was actually confirmed. Okay, let me define what spin is. Spin is essentially it originates from the idea of angular momentum, but it's not the ordinary angular momentum that you know. Okay, the ordinary angular momentum is normally called orbital angular momentum. It comes from rotational motion. But spin, also some people think of a particle spinning. Even this is wrong. Okay? This is actually a wrong picture. A spin is just it's like in a way, it's like a birthmark. Each particle will have its intrinsic spin. Okay. So if you belong to this type of particles, you have spin half or spin 0 or spin 1. Photons, for example, will have spin 1. Okay. Electrons will have spin half. Okay. Even photons, because of this being massless, you have only two different quantum states. Okay, and then so this is plus massless property. So the basic quantum states are just two states. And you probably heard about these two states. It's called polarization. So you can have vertical polarization or horizontal polarization, or right circular polarization or left circular polarization. So you can have different types of polarization, but the only state a photon can be in is these two types of state. Okay, either horizontal polarization or vertical, or you can use other types of polarization, but there are only two types of polarization. And the same thing happens over here for electrons. Okay, electrons have spin half. And remember, this is again, it's not like your angular momentum which has this motion. It doesn't have any motion. It just comes with that electron. Okay, it's like like I say, it's like a birthmark. So electrons will have this birthmark called spin half. Okay, so this spin half, and spin half will have two natural quantum states, spin up and spin down. Okay, and in fact, because of this simplistic nature, there are only two fundamental states with respect to the spin state. Okay, one can write this spin operators, so-called. So since it's like angular momentum, it has okay, maybe I write it down first. So you can have components of it as x, as y, and z. But these operators, because of the finite nature of these spin states, can be written as, so let me just take the simplest case of sz. So this is all the operators here. Okay, your sz will have a 2 by 2 matrix given by 1, 0, 0 minus 1. Okay, and you can see that the states corresponding to this state, eigenstates, corresponding to the, okay, please don't fail me now, Control Z, your SZ operator, the spin Z operator, okay, will be just simply what we call the spinor states in this case. What am I doing? Okay, maybe I write in this way: psi up, which can be written as a matrix 1, 0, and psi down, which you can write as a matrix 0, 1, and you can essentially write down the eigenvalue equation in this way. Okay, slowly, h bar on 2, psi 1, and then sz. So this is supposed to be up, yeah. Psi down equals to minus h bar on 2, psi 2. And this is probably the simplest that one can get in terms of quantum states. Only two levels. Okay, you have spin up or spin down. So there will be simple examples that we can use to demonstrate some statistical mechanics idea, and I probably want to do this in the next lecture rather than do it now. Okay, so I'll stop there for today. Okay, so I hope it doesn't confuse you too much. So, but the idea is you introduce this idea of spin that has two states only, and it allows you to be allow you to make simple examples out of that two spin, two quantum state thing. Okay, so let me just take the attendance before I go. My computer, so when you have a 2-hour lecture, it really gets slowed down. Come on. Okay, that's done. So I'll stop now. So if you have any questions at this stage, you can ask before we end. I guess no. All right, so we end our lecture today. So I will stop. Thank you, everyone. And I will message in WhatsApp when the assignment is ready. Okay. Okay, bye everyone.